Hello, everybody. Today our lesson will be on critical values and the first derivative test, day 2. Yesterday we discussed how we can use critical values and the first derivative to help us determine where a function is increasing or decreasing and where a function has a relative maximum or minimum value. Our focus was primarily on polynomial functions. Today we're going to extend our study to include more complicated algebraic functions. We're going to follow the same process as yesterday, but we will deal with the second type of critical value. So let's stop for a second and let's review what a critical value actually is. We said the first type is when we set the derivative equal to 0 and solve for x. Okay, this type of critical value usually occurs with polynomials. The second type of critical value is where f prime of x is undefined, but f of x is defined. Okay. This may seem a little bit confusing, but as soon as we do an example, you'll be good to go. This type of critical value is usually found when we're dealing with rational functions and radical functions. Okay, so let's just kind of review for a second. A rational function is when I have one function over another function, for example, something like this. And a radical function is when you see a square root in the function, which we know we can rewrite as a fraction power. So something like the square root of x would be x to the 1/2 power. All right, so I'm going to try to do an example of each in this lesson so you'll have a better idea of what's going on. So for the following functions, find the critical values, which we know is f prime is equal to 0 or f prime undefined, and we're going to put those critical values on a number line, just like we did yesterday. We're going to identify where the intervals on which the function is increasing or decreasing. Remember, increasing means the derivative is positive. Decreasing means when we test in the derivative, we get a negative value. And then we want to talk about any relative maximum or minimum values. And a maximum occurs when we go from a positive to a negative interval, and a minimum occurs when we go from a negative to a positive interval. So let's look at our first function. Y equals 1 over x squared. I wanted to stay with something basic so it would not take too long to finish this lesson. When I look at this function, I know I have to take the derivative to get the critical value. So I can either use the quotient rule or I can rewrite this. I would probably rewrite this function because now I can just use my shortcut method or my power rule. So my derivative becomes negative 2x to the negative 3rd power. And now this is why it's so important for you guys to understand why we rewrite with a positive power. This is the rule for my derivative right here. Okay. And now we're going to use this rule to move forward. When I look at this derivative, I have a top and a bottom. I have a rational function. So basically, I need to find where the derivative is 0 and find where the derivative is undefined. To find where the derivative is 0, basically, since it's a rational function, I want to set the numerator equal to 0. So I take and I set negative 2 equal to 0. If you try to solve this equation, negative 2 can never be 0, so we don't have a critical value there. That's okay. Moving on to it being undefined. When we're looking for where a function is undefined, we want to set the denominator equal to 0. So I take and I set x cubed equal to 0. Where is x cubed equal to 0? Well, that's when x equals 0. But now I want to take this value and I need to plug it back into the original. And I notice here it's undefined. So technically, this function is not a critical value, but we still have to test it. okay? We're still going to test, meaning I'm still going to put it on the number line. So I move back up to where my derivative rule is, and I make a number line for myself. It's a y prime number line I'm testing in. And I'm going to take, and usually this is going to seem a little weird at first. I put this, I want to remind myself it's technically not a critical value, so I make a little squiggle around it. And I take and I plug a number that's less than 0 into this. So let's say I take a negative value, -1. If I look at my derivative function, my numerator is always going to be negative. And if I cube a negative number, my denominator is going to be negative. And a negative over a negative gives me a positive answer. So this interval gives me a positive derivative, which tells me my function is increasing. If I move over to the other side of 0 and I plug in a number, let's say 1. If I go plug that into my derivative, I'm going to have a negative in the numerator. And when I cube a positive value, right, I get a positive number. This gives me a negative for my derivative value, which means my function is decreasing. Okay, so for this so far, for part A, there were no critical values. Okay. Even though I got an answer here, it's technically was not considered a critical value, but you still have to test that number. You still have to make a number line. For part B, where is this function increasing? Well, the function is increasing strictly by my number line from -infinity to 0. Where is this function decreasing? Well, this function is decreasing from 0 to infinity. Now let's talk about any relative maximum or minimum values. If I'm trying to decide for any relative max or relative minimum values, remember, those are turning points in our graph. It looks like I have a turning point here. I go from positive to negative, but I will not have a point because my function is undefined. So in this case, even though we go from a positive to a negative interval, there are no true turning points. Okay. So I know that's a little bit confusing, so I'd like to look at the graph of this function so we can make sense to what's actually happening here. If I go into my calculator and I look at the graph of y equals 1x over x squared, I see it matches up with my number line. The function is increasing. The function is decreasing. The function has no max or min because where my graph changes from increasing to decreasing is actually an asymptote, okay? And remember, our values where the function is undefined can either be asymptotes or holes in our graph. So this particular value was an asymptote. So that's an example of something that involves a rational function. Let's look at something with a square root sign or a radical. If we look at our next example, f of x equals the cubed root of x minus 1. When I look at this function and I'm deciding what to do to find the derivative, I know right away I can't take the derivative of a radical sign. So I'm going to rewrite this as a fraction power. Now I'm going to differentiate, and I'm going to use the chain rule because I have something being raised to a power. So the derivative of the outside, when I subtract 1, I get negative 2/3, times the derivative of the inside, which is just 1. I'm going to clean this up and write it with, it's probably best to use a fraction power here. So my derivative is 1 over 3 times x minus 1 to the 2/3. My derivative has a top and a bottom. So I know I have to find where the derivative is 0 or where the derivative is undefined. Going back up to the derivative, set the numerator equal to 0, set the denominator equal to 0. Okay. We know this can never happen. No critical value. That's not always going to happen. It just happens to be the case in these examples. Over here, when I go to set this equal to 0, to find where it's undefined, I can divide by 3. And now I raise each side to the reciprocal power, which is 3/2. And x minus 1 equals 0. X equals 1. So now x equals 1 is where the derivative is undefined. Now I want to see, when I plug this back up in my original function, do I get an answer? And the cubed root of 0 is 0. So yes, this is a critical value. Okay. Now all that means is I know this number's going on the number line, right? These values only give us the values that we're going to put on the number line. Go back up to my derivative, and I want to make myself a number line to test in. 1 goes on my number line. I'm going to take a number less than 1. Use 0. It's the easiest. Now here, this is easy. My numerator is always going to be a positive number on either side. Does not matter. The denominator, if I plug in 0, I get a negative in a negative inside parentheses. But think about what you're doing. The cubed root of a negative is a negative number, and I square it, it's going to be a positive value. So the derivative test is positive, which means my function is increasing. On the other side of 1, let's say I take 2. Again, plug it in here, I get a positive value. Cubed root of positive, positive, square it, positive. Increasing. Okay, so now this is going to seem a little weird, but let's just go through the steps. Our critical value, answer to part A, was at 1. For part B, my function is increasing, my function is decreasing. My function is increasing from negative infinity to infinity. And my function doesn't ever decrease. Okay, that's not a big deal. I just want to point out here, the function is increasing over the entire interval. I can write it this way because f of x is continuous to begin with. Okay, if f of x was not continuous, I would have to split up. I would have to split this up into 2 intervals. Okay, so you have to be careful there. And now let's look for any relative max and mins. And again, here, how do we identify a max or a min? It's where our derivative test on our number line goes from a positive to a negative or vice versa. We're not going to have any relative maxes and mins either because our function is increasing over the entire domain. Now, you would not have to really write these so descriptively at this point in time. I'm just kind of trying to explain things in more depth right now. Let's take a quick second and see what's happening with the graph so we can make sense of the calculus we just did. So if I'm going to plug in, let's say I do, x minus 1, sorry, I still have it from the other, and we're going to raise that to the 1/3 power. Remember, that's our original function. If we look to see what the graph of this function looks like, if you look, it matches. It's increasing over the entire domain. Okay, there's no asymptotes or anything like that. And our function has no maxes or mins. It has no turning points. Okay, and that's all we're doing, is we're just analyzing our number line and coming up with the answers to the question. One quick note I want to make to all of you: a relative max or min has to be a critical value, but A critical value does not have to be a max or a min. Okay. So that's something you may want to consider when you're working through the homework examples for tonight. Thank you and goodbye.